All right, good morning or good afternoon, folks. This is day 2 of L'Hopital's rule. So what we had talked about yesterday was this really cool concept that after doing as much work as we did to figure out how to work on limits, and then we did some derivatives, and then we kind of took the limits and we kind of set them aside, and we hadn't touched limits for, seems like months now. Then we come back and then suddenly we reintroduce this concept of limits. And we realize that it kind of comes full circle, that we can use derivatives in order to evaluate limits whose initial outcome is the indeterminate form 0 over 0 or infinity over infinity. Now, really quick, just a couple of things I do want to point out. There are a couple of indeterminate forms that exist that we've not really played with. Some of the ones that I'm thinking of in particular are situations where I actually get limits on occasion that will give me things like 0 times, and let me just real quick, these are indeterminate forms. Indeterminate forms. So a bunch of indeterminate forms. Of course, we already knew 0 divided by 0, and we knew infinity divided by infinity. But there are actually several other indeterminate forms. Anything that's in the form of 0 times infinity. Essentially what you want to do is you want to almost think about this idea that, that one piece of the problem is telling you to go to something, and another piece of the problem is telling you to go to the complete opposite. For instance, 0 over 0. If I multiply by 0, a function goes to 0. Every time. Don't have a choice. You're stuck there. But if I'm dividing by 0, then ideally as I'm taking that limit, the idea is that the number is getting incredibly large and that the number is growing without bounds. So if a limit approaches something over 0, then my number goes to infinity. Every time there's no choice. But what happens if I have to go to 0 but also have to go to infinity? Same exact concept with infinity over infinity. The multiplication of infinity should take me to infinity, but a division by an infinity concept should take me to 0. So I don't have a choice. Well, that's the same thing as 0 times infinity. And we could get something like infinity minus infinity. Now that's a weird one, infinity minus infinity. That seems like that should be 0, shouldn't that? Well, actually, it depends on how big of an infinity I'm looking at. And for those of you who are really interested in that, there's a really good video that deals with infinities that I will share with you towards the end of this that kind of deals with the, I'll tell you what, I'll give you the name of it right now. It's called the Banach-Tarski, and a couple of people have already heard of this. But if you look up a video for the Banach-Tarski paradox, it does a really good job of kind of introing this concept of infinity minus infinity, much better than I could in the time span I have. Another one is 0 to the infinity, which seems dumb because it's 0 times itself a bunch of times. But if it's actually a variable that leads to 0 to the infinity, remember that the variable never actually equaled 0. It equaled something very, 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 very tiny. So anything to a number that's not will go to infinity, and it gets all sorts of crazy. The two that we're focused on is this, and in fact, L'Hopital only works here, so any other of the other ones that come in, we need to turn into 0 over 0 or infinity over infinity to make them work. Now, sadly, there's several of these questions that I didn't realize were on here at the time that we actually cannot answer. For instance, we actually can't do any of this problem, and that actually all comes down to the fact that we've got this weird squiggly line symbol. You'll notice that's on the t-shirt. That's an integral, and we are nowhere close to that. In fact, what's going to wind up happening is this requires a specific theorem that connects the idea of an integral with the derivative, and we're not going to get to that for at least a few days, probably not until after Thanksgiving break. So it's there. It's something that we need to be aware of, and we'll look at that eventually. What I'd like to do then is I would like to look at the 2016 AB4 question, and I'd like to answer that one. So consider the differential equation dy dx is equal to y squared over x minus 1. Now, this is something that you have to get very used to, is in calculus, a lot of times I'm going to do something called an initial condition. And the initial condition is just kind of slapped in the middle of the problem just to mess with you terribly. And what I mean by that is when I go to evaluate this, eventually I have to take the limit as x approaches 2 of f of x minus 3. And some of you are still hurting from this particular question. If you recall from a testing scenario, I believe it was the last test we took, where you had a situation similar to this, and I gave you an initial point. Well, here it is again. The limit as x approaches 2 of f of x gives me the f of 2, which is 3 minus 3, which is 0. And then, of course, the limit as x approaches 2 of x minus 2, which is also 0. So now that we have those, and we can prove that we have a 0 over 0, I can take this and I can look at the limit as x approaches 2 of the derivatives. Not x approaches 0, x approaches 2. My apologies. So the derivative of f of x is f prime of x minus 0 over 1. But what is f prime of x? Well, the limit as x approaches 2 of f prime of x really is the f prime of 2. And the f prime of 2, if I look over here, if I look at this relationship y equals f of x, well, the derivative of y is f prime of x. So I really want to know what dy dx is evaluated when x is 2 and y is 3. And I got that 0.23 from the initial condition. Oh my gosh, why is there so much stuff going on here? Well, dy dx at the 0.23 becomes 3 squared over 2 minus 1 is 9. Notational fluency is going to be important. Understanding, be able to connect f prime with y, with dy dx, with f, with the initial point, with limits, and oh my goodness, there's a lot going on. So let's take a look at another one. Again, anything with the squiggly line, we're omitting at this point. For this second question, I'll tell you what I'll do is I'll give you a moment to pause the video and try it out yourself and hit play when you're done. All right, hopefully you paused the video and you started this up. You should have, as initial thing, is to evaluate these limits. I believe in writing like this, mainly because if I do this, if I need L'Hopital's rule, it's really simple to realize, hey, L'Hopital's rule applies. Cool, because I got a 0 over 0. I've done my separate limits, so I'm good to go. If I just start plugging things in beforehand and I don't get 0 over 0, or if I do get 0 over 0, I've got to go back and rewrite this, and it's dumb, so we don't want to do that. So I take a look. This becomes the g of 6. Oh my goodness, I can't see. Hold on. There we go. G of 6 is 3 minus x at minus 2 minus 1, so this is a 0. And f of 2 is 2, so I get 2 minus 2, which is 0. Cool. I can do this. This is nice and easy. Limit as x approaches 2 of g prime of 3x times 3 minus 1 over f prime of x. So when I evaluate this limit, I have 3 times the g of 6, g prime of 6 this time, so g prime of 6 is negative 1. So I've got negative 3 minus 1 over the f prime of 2, which is negative 2. My answer turns out to be 2. We like L'Hopital. L'Hopital is our friend. He makes things go much quicker when it comes to limits, assuming you're good at taking a derivative. So be aware of that. Got to be able to knock out those derivatives as we go. This question, I don't see any of the things, but we're actually talking about areas. And again, we cannot do anything with u. And there's a little squiggly line, so we can't do anything with u. We can, however, do question number 5 here, so let's go ahead and find this one. If you're flipping through your pages, because I went through those two relatively quick, I will give you a moment to find it and try it out. So please pause this video, give it a shot, and then I will go through it. All right. So, as always, we start off with a nice, easy setup. Just see what we get. The limit as x approaches negative, f of x minus 8 approaches negative 1. There we go. So I find the negative 1, and I find out that this is 8 minus 8. And the limit as x approaches negative 1 of 2 to the g of x. Okay, not looking forward to that. All right. G of x at negative 1 is 0. So 2 to the 0 is 1. 1 minus 1 is 0. We've set ourselves up for a problem that uses L'Hopital. That means that we need to take the limit as x approaches negative 1 of the derivative of the top, f prime of x. Numerator is nice, easy derivative, but you need to remember the derivative of a log problem. So I take a look at this. This becomes 2g of x. The derivative of 2g of x is 2 to the g of x times the chain rule times the natural log of 2. Holy moly, the derivative of the, oh man, okay. Let's do this. All right. So the limit as x approaches negative 1 of f prime of x is 0. Ooh. Over. Now as long as this denominator doesn't go to 0, we're happy. So let's see what happens. 2 to the 0 is 1. So we get 1 times g prime of negative 1 is 3/2. Oh good. Times the natural log of 2. I'm cool with that. The whole thing goes to 0. By the way, on this, because it's a free response, just giving you a heads up, this question you would definitely get, points for taking this derivative. There's definitely going to be a point for that, and then there will be a point for an answer, and they might give you a point if you try to do the problem, but you forgot the natural log or something like that, but you still wound up with 0. You were attempting L'Hopital, they would probably give you the point, even if you did the derivative wrong, as long as you showed your individual limits. I believe the next question is also omitted because it talks about areas, and we can't do those yet. We'll be able to do that question fairly quickly, fairly soon. So that's coming up, and that is all I have for you, folks. I'm hoping that you're feeling pretty strong about L'Hopitals. I need to check, but I believe there will be a formative on this. Quickly, we'll probably do the formative before we do the play thing on Wednesday, just because we need to. Please don't forget to bring your calculators tomorrow. Incredibly important that you do so, because tomorrow, remember, is going to be a literally just play with the calculators. I know they're unfamiliar with you if you haven't touched them yet, or you're too terrified of how the heck this thing is all set up. I promise I can help you get you started with it, get you in a position where you can feel successful with it. We'll play with them tomorrow so that we can use them for calculus starting Thursday. So I hope that this was useful. I put up a L'Hopital rule worksheet up on Schoology, so that is there for you to work on. Hope you have a great day.